Yeah, thank you very much. So first of all, I would like to thank all of you for still staying after 5 long talks with me. And then most importantly, I would like to thank the organizers for the opportunity to tell you something about some process generating random permutations that I've been working on for some time, and I will try to show you that this is an interesting process, there are interesting results there, and hopefully you will find this exciting. So, today we have heard in the morning the talk by Percy Diaconis, who was talking us something about processes of card shuffling. When I'm teaching computer science students, often in the first year, one of the first procedures I want to show students is how to generate random permutations. And there are many ways of doing this, but somehow, for example, one of the most natural one is that you have deck of n cards, or you have n elements. You just choose one at random. You are saying this will be the first element, and you recursively run the same algorithm for the other elements. So this is something which students, for example, are very happy to implement. Then they are finding that it's easy to analyze, it's easy to understand, and they think often that actually it works well in practice, which is often not really the case. So first of all, if you really want to implement it, you have to generate random numbers between any range. So say from 1 to n, or from 1 and all other small numbers. Then you have to repeat this n times. And if you want to use it in real practice, so if you want to use this for card shuffling, it's kind of a very slow process if you try. Try to do it for 25 cards in a bridge. So we have also seen some other processes that, for example, Percy been talking about, or some other speakers he were presenting. So I would like to think about some way of generating random permutations, which is very fast. Hopefully it's faster than doing this in n rounds. It's simple, it shuffles well, but it's also to some extent local or distributed. So, for example, that we can just build easily some machines which will easily be able to do it quite quickly. So there is a framework that I want to present to you, which I called generating random permutations using switching networks. And again, here I will have the following kind of premises. I want to have a way of generating random permutation in an oblivious way, and later I will explain what I mean by that. And I want to do it using networks as underlying machinery. So now, I don't really know whether many of you have seen sorting networks, but what I want to do is something very similar to what people are doing in sorting networks. So a sorting network is a network which is using something which is called as switches. So a switch is something that you have 2 inputs, 2 outputs, and the output on the top is the smaller of the 2 input numbers, and the output at the bottom is the larger one. And in late 70s and 80s, there have been quite a lot of study of how can we sort numbers using sorting networks. So the idea is that you want to have a network, and you're saying whatever is the input configuration, at the end, if you run sorting network through it, at the end you will get sorted sequence. And there have been some deep study in computer science about that. And there are some beautiful results. We would like to do something similar to generate random permutations. So what do we mean by that? So we would like to use the switch as in the sorting network to just decide about random outcome of 2 arriving elements. So, I have a switch which I will try to draw in that way. So there are 2 elements arriving, and then I toss a coin. And if there is a head, I will not change the order. If there is a tail, I will change the order. And now the question is, can I set up some good networks which, using the random switches, which will be able to generate random permutations? Okay, so here is an example of a network, of switching network. So, I have elements. So usually I will in this talk, I will always draw it as a layered network. So here I have layer 1, so I have 8 elements, and here I have random switches depending on the random outcome the elements will move forward to the right-hand side. So this is the way how people more often draw it. So, the process is you have elements, and then you just at random transfer them from left to right. So what are kind of important parameters of a network? So number of inputs, what is the total number of switches, and what is the depth, number of layers. So in this case, we have network with 6 inputs, 12 switches, and depth is 5. And of course, our main goal is we would like to generate something which is like a random permutation, and this will be our main goal. How can we do it efficiently? So what is the distribution of the output permutation? And we would like to generate networks that will generate random permutations. Now, maybe you can think that this is some kind of an odd construct, but actually people have been studying this mostly because of applications in cryptography. So in cryptography, they have some Moni Naor. He was kind of the first who observed that if you have such a network, and you can kind of hide the information, so hide the information about the way how the element is transferred from left to right, and then somehow, in order really to detect what is the output, you have to reveal very many of the switches, which is because of some reasons kind of difficult to do in crypto systems. So really the motivation is, I would say, is coming from, one motivation is coming from cryptography, another, there has been some uses in distributed computing. And also the point which I want to make here, there are also many natural card shuffling schemes which can be represented in this framework. I'm not sure whether many, but at least one. So there is this Thorp shuffle. So today, Percy Diaconis was talking about riffle shuffle, which is a very efficient way of shuffling a deck of cards. And if you think about regular bridge players, poker players, this is the way how they are kind of trying to do it. So you take a deck of cards, you approximately half and half, and then you use, as formally it is described, you use, I don't know, binomial or some distribution, how you shuffle the cards. If you really want to do it in an algorithmic way, or maybe if you want to build a system, the fact that in riffle shuffle, so if you are doing this, you kind of have complicated probability distribution, how you'll shuffle the cards. It's making things complicated. So Thorp shuffle is doing it in a much simpler way. So what is Thorp shuffle doing? So you have n cards, you cut the deck into 2 halves, and then you do the following thing. You take the first top cards from each half, and you decide at random which one will be taken. Then you take the next top cards, and you repeat this. And in this way, you kind of shuffle, you shuffle the whole deck, and you repeat this. And the natural question is how many times you have to apply the shuffle to obtain something which resembles random permutation. Now, there is a very close relation between Thorp shuffle and butterfly networks. I don't really know if you know butterfly networks. So butterfly networks looks like that. So you have 2 to k inputs. So kind of on every layer, you will have 2 to k nodes, and they are labels with binary representation of numbers from 0 to 2k minus 1. And then somehow, on layer 1, you will just have a switch between 2 elements whose last bit differ by 1. On layer 2, you will have a switch between 2 elements whose second last bit differ by 1, and so on and so forth. And then this process is equivalent to Thorp shuffle. One can show it in the sense that if you apply log n time Thorp shuffles, you'll get exactly switching networks which correspond to butterfly networks, where n is the number of inputs. Okay, so so there has been some study of Thorp shuffle. I don't know if many of you are familiar with or not. There has been some conjecture that log n square layers in butterfly networks will suffice, or log n square Thorp shuffles. For a long time it was unclear whether we can get polylogarithmic. Then Ben Morris, he came first to log, I think, to 30-something. Then there was a paper by Prasad and someone else who improved it to maybe 17. Right now we have quite good bounds. So this is something like log cube or log to the fourth. Log cube is only if n number of inputs is a power of 2. Okay, so what I would like to study here. So I would like to design good switching networks which will generate random permutations. Good, I mean I want to have the number of layers is as small as possible. And just this star, I use it for here once. I want to make sure that the output, so the total variation of the output permutation will differ by, actually in my case, this will be polynomially small from the uniform distribution. Okay. So Rakov and Simon, they have been interested in networks of this sort because of crypto applications. And they showed many years ago that if you want to permute only 0 and 1s, so your input consists of 0 and 1s, then after polylogarithmic number of layers, almost every switching network will generate a random permutation of 0 and 1s. Then with few people we kind of show that if we want to permute 0 and 1s, we can actually reduce this to logarithmic number. However, our main goal was really not only 0 and 1s, but arbitrary permutations. So I remember, so if any of you is familiar with sorting networks, there is a beautiful result about sorting networks, which says if you can sort 0 and 1s, you can sort everything. So, our premises was maybe we can actually have similar theorem in the case of random permutations. We don't know if anything like that is true. So for some time I thought actually that there is a chance that the result of this sort is possible. I don't really know if it's true. So somehow you have a network which sorts randomly 0 and 1s, and I want to say, okay, this will also randomly permute. Or maybe you will have to repeat it a few times. So I want to, so for some time I thought actually that the result is true. Now I'm less sure if anything of that could be possible.
When
yes?
you say whether it, do you mean in the same length, or are you going to extend it to permutation?
So maybe apply it few times the same network. So maybe I have network of depth d, and I'm saying it randomly permutes 0 and 1s, and I'm saying I repeat it 10 times, or some number of times, or even log n times. Even log n time, yes. I don't know if this is true.
Seems obvious, but maybe.
Yes, I have been. That's what I thought a long time ago too, and I know some other people thought too. So.
I'll try to convince you after the talk.
Okay, excellent. Okay, so I want to show you the following result. So I would like to prove the result that there are, so almost every network of logarithmic depth will randomly permute numbers. And all what I can show right now is that it will randomly permute almost all numbers. Okay. So there are kind of two main results here. So first one is almost every network of logarithmic depth will randomly permute 99% of the elements. And the second result is that actually we can construct such networks. So one thing is that this is true for almost every network, and the second one is that we can construct such networks. And then actually, okay, so if you like k-wise independent permutations, the result is that you are generating 1 minus epsilon n wise independent permutations. And then using this, it's not actually difficult to show that there are switching networks that in total will have n log n switches and will randomly permute all the elements. So once you have the claim for 99%, you can extend it to all elements, but the depth is increased. At least I don't know how to not increase the depth.
That's the polynomial error always, is it?
Yes. So error is always polynomial. And also, we had some similar result for Thorp shuffling, which I will not be really talking here about, but we can show that if we have depths for the log n square, we can again randomly permute 99% of the elements. Any questions? Okay, so I want to now show you kind of the main results. So we can, for almost every network, switching network of logarithmic depth, we will randomly permute 99% of the elements. So almost all switching networks means we're kind of excluding, say, a fraction of 1 over n squared networks. Now, one should understand, I mean, there is a very important distinction between some other result that I will mention in a second, is that we're kind of fixing the network in advance. So kind of the game is as follows. Someone is giving me the set of all possible switching networks of logarithmic depth with perfect matching in between every two layers, and I'm kind of taking one of them, but then it's fixed, which means I cannot use the randomness coming from the fact that this switch, somehow it's like a random because I'm choosing random network. So somehow the input is a network, and for this network I'm showing that it will randomly permute 99% of the elements. If the result was different, when switches in every phase were chosen at random, then it's kind of easy to show that we can randomly permute after log n steps. So somehow if in every step you are just saying, okay, give me a perfect matching, or actually a matching of linear size between switches, and you repeat this, then it's not very difficult to show that log n steps will suffice. So here we are kind of fixing a network.
The vector, it's a constant number. If you are really matching, then
maybe even 3.
Yeah, but then you have to actually do the switch, not lazy switches. So lazy. If you do a random matching and you do the switch.
Yeah, but okay, so here I want to have that with probability 50%. And then I need log n because I won't be able to do anything faster than log n steps. Okay. And kind of how we are attacking this issue of almost all switching networks, we're kind of showing that almost all switching network is something like an expander. And then we're really analyzing this in the language of expanders. Now, what does it mean expander here? So it's a well-known fact that if you, I mean, we can interpret a well-known fact in our language so that if you are looking at any, say, 5 consecutive matchings or layers, and you are graph induced by these layers, then this graph for almost all switching networks will be an expander. So yes. Now what do I mean exactly is the following thing. So let Mi be the matching between layer I and I plus 1. And we define GKS to be an undirected graph with n vertices, so that I'm looking at matchings MK, MK plus 1, the S following matchings, and I'm just saying where can I come from a given vertex to any other vertices using these matchings, using the path. And I define the graph in that way, and then the claim is that the obtained graph will be expander. And here is an example. So for example, if I'm taking graph this G23, which means I'm taking layer 2, I'm looking at this vertex, and I'm looking what are all vertices which after 3 steps can be reached from that vertex. Then I will just connect this vertex to these vertices, to the 6 vertices. So as you see, you may have parallel edges. You will have actual parallel edges usually. Okay. So it's not difficult to see that for almost every network, this graph will be an expander. And we want to use this later. Okay. So now I want to explain to you how, kind of what is the method, how we are proving the result. So we'll be using coupling, actual non-Markovian coupling. I'm assuming most of you, if not all of you, are very well familiar, but still I will say kind of what we want to achieve here. So we're running two copies of the process, pi t and pi t star. And we're assuming we are starting with two different inputs, pi 0 and pi 0 star, and we have transformation so that both of them, pi t to pi t plus 1 and pi t star plus pi t plus 1 star are following the Markov chain. And our goal is to kind of couple these two processes so that pi t will be equal to pi t star for as small t as possible. That's what coupling is doing. And then we have the theorem that if they are the same after t steps, so if with good probability they are the same after t steps, then the chain will mix after t steps. Okay? So now we'll have one very nice simplification by called path coupling. So we can assume that actually these two elements differ by just one transposition. So kind of they differ only on two positions. So this is the first thing. And then we'll slightly lose in our bound. And the second thing is, here we'll be actually using this non-Markovian thing, which means traditionally when you are defining coupling, you are kind of saying, okay, first I'm looking at this transition, then I'm looking at this transition, and so once I have this transition, I'm deciding about coupling on the basis of this transition at once. But he will be doing this at the very end. So somehow we'll be first looking at the whole sequence in one chain, and only then we'll decide how the coupling will be set up. Okay? Okay, so suppose we have some network. Suppose we have permutations that differ by on two elements, and we want to permute only 99% of elements. So we have some number of zeros or jokers, which we'll be using as kind of a buffer to establish the coupling. Okay, so here's kind of these two copies. Okay, they differ on these two elements. So now, if we are thinking about coupling, the best case scenario is that you have pi t and pi t star, and they differ at positions ij, and we have a switch between positions I and j. And then it's standard thing in coupling that we can make sure that actually this pi t plus 1 and pi t star plus 1 will become the same. You just use different outcomes of the coins. So our goal is to try to emulate it. What is actually the problem with this thing? Of course, the chance that we have two permutations that differ on two positions I and j, and that there is a switch between I and j is very tiny. So what we are trying to do, we try to increase the probability that this match will happen in the algorithm. So this will be our goal right now. And how will we do it? So we'll split the process into two halves. The first log n layers and then next log n layers. And we first run the process on the first permutation. Yeah.
You said the zeros are the jokers, right?
Yes. So as I'm saying, we want to permute 99% of the elements. The rest are zeros. Okay, so yes. Okay, so we will try to construct a configuration that will increase the probability of a match between the switches. So what we'll do, we'll kind of have two stages. In first stage, so we start with positions alpha and beta, where the two permutations differ. And we are kind of saying, okay, we'll have a large number of positions where alpha can happen, and then we'll have a large number of positions where beta can happen. And we'll make sure that the probabilities are right, that this will be everything suitable for coupling. And then in stage two, we'll just say, okay, once we have this large number of positions, that there will be a matching between these positions. And once we have that, everything is done. Okay? So let's go into details. Okay, so this is stage 1. So what we are doing in stage 1, we want to kind of have this, want to increase the number of positions where these elements differ. So we'll be doing this building some full binary trees. So we'll have one binary tree starting at position alpha, another at position beta. Now, all these trees will be fully binary trees, will have the same depth. So all of them will have 2 to k leaves, which will be a linear number. And kind of the idea is that if we set up all the switches in network outside this tree that I will show in a second, then somehow the probability that this element alpha will reach any of the leaves is uniform, and the same is for the element beta. Okay, so here is kind of an attempt to draw it nicely, which is always a problem. So I will just show this only for one tree. So we have this element alpha, which is here. And now we are waiting for so we are running a random process, and we are waiting for the very first time this element will hit a 0, will be switched with a 0. Because we have linear number of zeros, we know that this will happen quite quickly. So at some moment this will happen. And right now we are not fixing the outcome of the switch, but we are fixing outcomes of all the other switches. We're running the process. But this kind of is frozen. And then we are again waiting for the branches when we'll hit another 0. Oh, this is 0. And we are running this, and we are trying to construct such a tree of depth k, where k is logarithmic in n. And what will be the feature of this tree? Okay, so the tree kind of will look like this. And the key property is that assuming I fix all the switches except the switches between these two elements, so this is fixed. And right now I'm saying, if I set the switches uniformly at random here, where this element will happen? This element will have uniform distribution to reach any of these positions. Okay? Why this is so? Because this is the way how we're constructing the tree. Okay? So now for coupling, this will mean that once we fix everything outside that, we have uniform position that alpha will reach any of these elements. The same will happen for beta. Okay? So, and then one can show that one can prove that actually we can always create with high probability, we can create trees with these properties. If we have almost every switching network, or in fact in an expander. And now once we have these trees, we want to use these trees, so the leaves of the trees, in the second phase, because these are possible positions where element alpha could be distributed and element beta could be distributed. And we are making observation that in this network right now, so this is, the yellow elements are from possible position for alpha, gray are for beta. And right now we're saying in the next logarithmic number of phases, we'll have a matching, or matching in the following sense, we'll have a place where one gray element and yellow will meet, and we'll have kind of perfect matching between these elements. So we'll have 2 to k such positions when we'll have a match between the elements.
So question, in the definition of the nodes of your tree were places where you meet a joker, right? But I mean, you might not know where the jokers are after a while because you've had these switches.
Oh, no. It's so once
that you don't look at the red switches that are involved in your previous tree.
No. So I have So this is the second phase. This is the next t-half steps. So first I'm creating these trees, t-half steps, where t is the whole time that I'm looking at. And in the remaining t-half steps, I'm trying to find matchings.
But I mean, even in the first stage, strictly speaking, some jokers you may not know where they are anymore because you're not saying what happens at the nodes of the tree. Is that just?
Okay. So I have only one element in a single tree. I have only one element which is not a joker. So I know that all other elements are zeros.
Oh, I see. I thought you only had 1% of jokers or something.
Oh, but my tree is so all the leaves. Oh, this was the picture of the leaves. all these leaves were coming from jokers, apart from one. So this is not a joker, and then I'm meeting a joker, and then I know kind of that these two elements, one of these two elements will take these two positions. Then I know that I'm waiting for another joker.
A different joker, I see.
A different joker, yeah, a different joker. So somehow here I have 2 to k minus 1 jokers, where this is a linear number.
Thank you.
Okay. So later I'm running the second stage, and kind of the result is that I will have a matching, and then I will be able to do exactly the thing that I wanted to do in the first phase. Where is the matching? Okay. Which means I know that I kind of can enforce the elements to be able to be in a switch. These two elements, where is the difference? Okay. And again, I can show that in almost every networks we can have such a perfect matching. So in short, what we are doing here, we have two phases. In the first phase, we are able to force the difference to have kind of different number of copies and in a uniform way. And in the second phase, well, what did I do? And in the second phase, we can coordinate the outcomes of these switches so that we'll be able to match them in the way how we wanted to have in the first phase. Okay, and then one is doing this, and we are able to show that by looking at these trees and matchings, we are saying that once we have the first sequence, pi 0, pi 1 up to pi t, that we can set the coupling for the stars so that pi t will be equal to pi t star with high probability. Okay, once we have this, we have our result. In the remaining few minutes, I want to show you something simpler. So once we have this, actually, it's not very difficult to show that we can create a switching network with n log n number of switches, but with depth which is log n square. And this is kind of, so first it was observed by Morris Rogaway, but this is kind of something which is not very complicated. So we have this network, and we know that it randomly permutes, say, 50% of the elements. So what we know about these elements here, okay, they are randomly permute, and they are random. So now we are using the second network for the next n-half elements, and we are using the same result. And then we are using then for n-quarter, n-to-8, and so on and so forth. And if you count number of switches, you will see, so first of all, you will see that the depth is log n square, but the total number of switches will be still n log n. So this is something which again can be done. Okay. So altogether you will get the result I just told you. Okay. In the last slide, so when I start thinking about it, I mean, actually, so my original goal was I wanted to understand Thorp shuffle. We have been trying to do something. All what we're able to do is to do it for 99% of permutations. I still think that I don't really know how to generate a switching network of logarithmic depth. I think it's an interesting question. And I still don't really know what is the mixing time of Thorp shuffle. Thank you.
Very much. Any questions or comments? Sorry, I have a very specific question. I've been wondering about this question for quite a few years, and maybe you know the answer. So, suppose you are allowed to choose the probabilities of the switches. A switch has probability p of switching the two elements, and in addition to choosing the network, I can choose these p's. And suppose I want to produce an exactly uniform permutation. Exactly uniform. Can you do it with fewer than n choose 2 switches? I know many ways to do it with exactly n choose 2 switches, and I don't know whether it can be done with fewer.
Very nice question. I don't really know. I think it might be challenging. So first of all, I want to, for some other audiences. I often actually making also a point that it is easy to see that this network will never generate a perfect random permutation. Unless it's of, I don't know, maybe, no, it never maybe. Because, yeah, so exactly, so because you have this probability 1/2 on every switch. So you always have to approximate the distribution. So this is a very good question, whether you can play anything with the switches, with probabilities.
I mean you can.
I know, but I'm just saying is whether you can do something.
Mm-hmm. But yeah, there are many ways to do it with n choose 2 switches, and I don't know whether you can do it with n choose 2 minus 1 for any n.